So, good morning, class. We will be starting in 5 minutes. So, if anyone is to join, they can join till then. Uh, we will begin at 5 p.m. So, in the last lecture, in the first interactive session, we were discussing some molecules. So, in the first interactive session, in symmetry elements and operations in some molecules, but due to some network issues and some recording issues, I couldn't complete the class and I couldn't take proper doubts, and the session was interrupted in between. But I will be sharing a recording for the first session. Uh, so I will be sharing a recording for the first session where I will discuss the problems on parity operators and some of the basics for these symmetry elements and operators. And in case you have any doubt, you can put it into ask questions of this course, and I will try to help you. So, so we are beginning today. So again, in this session, we will be covering all the symmetry elements, which is um, so the symmetry elements we will be discussing today are proper axis of rotation, and we know each molecule always have an identity operation that is always present within a molecule. So we will count it in each of the molecule, which is identity operator I am writing here. Third is inversion center, and fourth is improper axis of rotation. So the basics have already been discussed in the NPTEL lectures by professor. So here we will be practicing some some molecules where we will be finding these symmetry elements, and we will be counting the total number of operations present within a molecule. Okay, so let's start with the first molecule, which is CH3CH, chloromethane. So it will have tetrahedral geometry. So here we can see we have already discussed methane in the main lectures. So you know C3 is present in these molecules, and that passes through the principal axis of rotation present in these molecules is C3. So when we rotate these molecules in a 120-degree angle, so I'm representing it as as a triangle. These three protons H1, H2, H3. So let's say this is the carbon atom, and this Cl will be pointing upward, and one proton will be in the plane of these. This is the chlorine. One proton will be in the plane, and one proton will be coming out of plane towards you, and one will be going behind this plane. Okay. So what is happening here is these three protons, these are forming a 120-degree, these are having a 120-degree angles between them. And when we represent them in the form of a triangle, where this is the carbon atom I'm representing here. So this chlorine will be attached like this to this carbon atom. So as you can see, these three protons are making a triangle, and we can rotate them in a 120 degree at a 120-degree angle, which is C3 rotation here. And please take a note that C3 we can do this C3 axis of rotation either clockwise or anti-clockwise. Therefore, we will have two C3 axis of rotation. So we are doing it anti-clockwise here, and we are rotating this molecule with respect here. Like this is the C3x. Just a minute. This is the C3 axis, and we will be rotating this molecule. So the configuration will become S2, S3, and this H1. In Cl, because this Cl is on the axis of rotation, it will remain on its position. So these protons are changing their position, but the configuration we are getting is equivalent to the initial configuration. So, so, so this molecule has two axes of rotations, two C3 axis of rotations. One is clockwise and another is anti-clockwise. Now, Do we have another axis of rotation here? So here we will be checking C2 axis of rotation. So if you see here, is there a C2 axis collinear with C3 axis? No, because when we are rotating this molecule, this like if we give a 180-degree rotation, we are not getting an equivalent configuration. So these molecules which are 120, here we don't have a C2 axis of rotation. So now let us check the plane of symmetries which are present here. So we have three types of plane: sigma V, sigma H, and sigma T. Vertical plane of symmetry. This plane passes through the principal axis of rotation. And this is a horizontal plane of symmetry. This plane will be perpendicular to the principal axis of rotation. And this is the dihedral plane. This plane also passes through the principal axis of rotation, but it bisects the angle between two C2 axis of symmetries. C2 axis of rotation, sorry. So let us find out if this chloromethane has which type of plane of symmetry in it. So I'm again representing it these three protons uh, in form of a triangle here. So because if you press these, they will make a kind of a triangle. So it's just a representation to make to help you visualize this molecule in a easier way. So here we will have a vertical plane of symmetry. Uh, Firstly, we will check what is there a horizontal plane of symmetry. So this is the principal axis. And do we have a plane of symmetry vertical to it, which gives an equivalent configuration? No. Let us see what kind of a configuration it gives. So what will happen? This chlorine is above the plane in this representation. This will go down and give a configuration like which is not, this is not an equivalent configuration for our initial molecule. Therefore, we don't have a sigma H plane here. But do we have vertical planes here? Yes. So if you see, if you make a plane, consider it as a plane passing through one of the edge. So I'm labeling it. Pa this is a plane passing through proton 3, 3 and bisecting the plane, bisecting the plane bisecting these proton 1 and 2. So this plane has uh, protons opposite to each other. So this plane will contain this chlorine atom in it. So it will, if I represent it like this, so we have here similarly, we can bisect, we can do a bisection through proton 2 and proton 1. So therefore, we have three vertical planes here, three vertical planes passing through each of the proton. Okay, and carrying this proper axis of rotation, C3 on its plane. So here in this molecule, we can clearly observe we don't have a inversion center. So if you see, this is this chlorine. If we take, we have to take the inversion center on the central atom, which is carbon here. So I'm taking this point. So do we have a do we have a chlorine opposite to it? No. Similarly, do we have a proton like opposite to it? So we don't have a inversion center here. And if we see, like if we take the proper axis of rotation and take a and so we will be checking improper axis of rotation. So for it, you have to firstly do a rotation around principal axis, which is C3 here, and then you have to do a like reflection. You have to do a like this reflection along the perpendicular plane to it, to the principal axis. So here we will not get the equivalent configuration for this C3 followed by sigma H plane. So therefore, we don't have an improper axis of rotation here. So the total operations we have here are, which we also say order E, C3, C3 inverse, and 3 sigma planes. So we have total 6 operations. So here order, the number of operations in this molecule, symmetry operations here are 6. So the next molecule we will be taking so we will be taking BRF5. So BRF5 has square pyramidal geometry. And how do we represent it? These 4 fluorines are in the plane of the board, and this one fluorine is perpendicular to the plane of the board. Like this. So this is bromine. We have 4 fluorine, two in front of you and two in the back of this bromine. So we can represent it like this also. Okay. So here we have Firstly, we will check for proper axis of rotation. Here we have C4 axis of rotation. These four molecules have 90-degree angle. So if we rotate them at 90 degree with respect to each other, the configuration we will get is, so we got an equivalent configuration here. So we have C4 axis of rotation. And what are the other axis of rotation present here? We also have a C2 axis of rotation, collinear with this fourfold axis of rotation. And please note, since we have a C4 axis of rotation here, we can have it either, we can do this, perform this operation either clockwise or anti-clockwise. So we will count it as C4 and C4 inverse symmetry operation. Here, in the case of C2, we have, we will get on performing this operation, the configuration we will get is, so this is the equivalent configuration. So we have C2 axis of rotation here. Now we will check the plane of symmetries here. So this is a C3 principal axis, and we have this plane perpendicular to it, which carries this bromine and these four fluorine atoms. So if we perform a sigma H uh, operation here, do we get an equivalent configuration? So let us check what kind of configuration we. So we will get an inverted configuration here, like this. So these two configurations are not equivalent. Therefore, we don't have a horizontal plane here, but we have vertical planes present here. So I'm labeling these atoms. So we have this one sigma v plane. This is the first vertical plane. And please note this plane will carry this F5 atom in it, because we know that vertical plane always carries the principal axis of rotation, and this fluorine is present on the principal axis of rotation. Similarly, we will have another vertical plane like this. So I'm showing you the configurations we will get on performing these operations. So these are the configurations we get, and these are equivalent to our initial configuration. So we have two vertical planes. And we have two dihedral planes also present here. This is, sorry, sigma d. So what are the configurations we get after performing these operations? So we have two dihedral planes. And we don't have inversion center here in this molecule, because for inversion center we should have equal number of atoms present opposite to the center of, of the molecule on the both sides. And here we can see this fluorine. We don't have a fluorine present opposite to this fluorine. So here we don't have an inversion center, although we have fluorine atoms present here opposite to each other, but we don't have it here for this atom. Like the fluorine atom which is present above the plane of the board, we don't have a fluorine atom below the board of the plane. Therefore, so I'm removing these. So we don't have inversion center. Also, improper excess of rotation. So if we apply this like C4 axis of rotation, which is our principal axis of rotation, and these fluorine atoms which are present in the plane here, and this fluorine which is above the plane. So I'm considering all the fluorine atoms in the plane of my hand, and this one fluorine above this above my hand. So if I rotate these molecules, we have C4 axis of rotation. But after performing this operation, if we apply a reflection, if we apply this plane of symmetry like sigma h, a plane perpendicular to the principal axis, we don't get an equivalent configuration. We will get this fluorine atom below my hand, like below the plane of the board. Therefore, we don't have a improper axis of rotation here. So, the total symmetry operations we have in this molecule are identity operation, then C4, C4 inverse, C2, uh, two vertical planes, and two dihedral planes. So total we have 2, 3, 4, 5, 6. Order of this molecule is 8. So the next molecule is PF5. So it has trigonal bipyramidal geometry. So before finding out, so to find out the symmetry in any molecule, we should be aware of the right geometry of that molecule. Then only we will be able to find out the correct symmetries in that molecule. So here we have a C3 axis of rotation. which is our principal axis here. So what is the configuration we will get after performing this operation? These two fluorine atoms F4, F5 uh, are present on this principal axis of rotation, so they will have their position fixed. But these three fluorine atoms, they will rotate at 120-degree angle with respect to each other. It will get a configuration like this. So this configuration is equivalent to our initial configuration. We have C3 and C3 inverse because we can perform the C3 either clockwise and anti-clockwise. So two C3 operations, and we have C2 axis of rotation also here. So passing through each of the fluorine atom, we have a C2 axis. So we have three C2 axis along three fluorine atoms which are present, which are planar, I would say. So we have three C2 axis of rotation. So we have a horizontal plane of symmetry also here present in this molecule. Which contains these three fluorine atoms on it. So if we perform, so this is the plane which we so consider this as proton here, and this has one fluorine, another fluorine, and another fluorine. So we have one fluorine above my head and one below it. So we perform this horizontal plane of reflection along this horizontal plane. We will get a configuration like this. The configuration of these three fluorine atoms will not change, but these fluorine atoms will change. So we have a sigma H plane here, and we have three sigma V planes present along each of this C2 axis. and we have this uh, S3, improper excess of rotation, also present in this molecule. Rotation. Because when we perform this C3 excess of rotation followed by reflection along plane perpendicular to it, which is sigma h plane here. Here we will get an equivalent configuration. So let me show you how this uh, symmetry operation works. So if you have any doubt in between, you can just ask me. You can write it in the chat box, or you can unmute and just ask me in between. So this is the final configuration we will get after performing this S3 operation. So we got an equivalent configuration. So similar to C, so this S3 will also have clockwise and anti-clockwise operations, because if we are performing this C3 axis of rotation clockwise, then it will the S3 will be give results according to it, and similarly for anti-clockwise. So here we will get S3 and S3 inverse, clockwise and anti-clockwise. So the total operations here are identity operation C3, C3 inverse, sigma H, uh, and we have sigma V also, 3 sigma V, S3 and S3 inverse. So how many total operations we have? 2, 3, 4, 3, 4, 5, 6, 7. Yeah, and we have 3C2 also. So we have total. So the order is 12. So the next molecule is, um, we will be discussing this molecule. Uh, this first, lambda, lambda, cis, Cl2 positive. So this molecule, this cobalt, uh, cis dichloro bis ethylene diamine cobalt cation. So this is two enantiomers, which is for lambda. We have taken lambda here, and delta. So for the two enantiomers, we will get different configurations, different geometries. So what is the geometry for this molecule? So this ethylene diamine is a bidentate chelate ligand. So we will get a geometry like this. Cis difluoro this ethylene diamine for cation. So so the proper axis of rotation here we will get is a C2 axis of rotation. Okay. Uh, I'm representing this molecule another way. where these two CLs here, and these two. Sorry. Like this. So here you can clearly see a C2 axis of rotation present here. So how will we get how our configuration will change after this? So this NH2 molecule, this one will go above, this will go down, this will these will go this like this one will go back and this will come forward. So we will get a equivalent configuration here like earlier. So we have a C2 axis of rotation in this molecule and we don't have any other symmetry operation present here. So the total operations here are identity operator and C2 axis of rotation. So the order is 2. The next molecule is this one. So the configuration here will be this is a trans molecule, so we will have chlorines opposite to each other. So here the operations we have are an identity of sorry yeah we have identity operation always present, but we have an inversion center also, because if you see this molecule which is forward to the like uh, this cobalt atom, these two chlorine atoms are present in the plane of the board, and this amine group is coming forward and one is backward to it, like trans to it. Similarly here you have, so we have these amine molecules opposite to each other. If we perform this inversion operation, so we have this inversion center present in this molecule, and uh, we have proper axis of rotations also, which are, so we have uh, one C2 axis like this, and one perpendicular to the plane of the board. So we have C2, C2G, C2Y, and C2X. So three C2 axis of rotations are present, and also sigma H plane is present. So total symmetry operations we have here are identity operation, right? Uh, Inversion center, horizontal plane. So we have five, six. Sorry, we don't have horizontal plane here. Okay. Four, six. So this is the. So we have another geometry for this molecule. Another So the geometry for this molecule is, so here we can see a C2 axis of rotation present like this. Rotation, and we have E I sigma H. No, we don't have a C2 axis here. We have identity operation, then center of inversion, and do we have a sigma H horizontal plane here? Uh, we have this C2 axis and then a sigma H plane perpendicular to it. भैया मेरी क्लास चल रही है प्लीज जाइए आपको कुछ काम नहीं है तो वेरी इंपॉर्टेंट सॉरी फॉर द इंटरप्शन this is the sigma H plane we have present so here we have C2 operation sigma H present so we have order 4 for this molecule. Next molecule is Uh, we will be discussing this ethylene bromine chloride. So this is bromochloroethylene. So here I have taken a trans isomer. So here we can see uh, we have an inversion center present. At the center of the this double bond between carbon and carbon. So this is our inversion center. No, sorry, we don't have an inversion center. We have C2 excess present along this bond. So we'll have a C2 excess like this passing between these bonds. So the configuration we will get is after the C2 operation, these two hydrogens will change their positions. These chlorine atoms will remain as it is. So this C2 excess is coming out of plane. So we will have a sigma H plane present here, which carries the, which is the plane of the molecule. Or we can say the plane of the board here. This is a sigma H plane here. So we have a C2 axis in sigma H plane, and sigma V plane passing through C2 axis. So do we have improper axis of rotation? S2 here. So it will be S2 will be C2 sigma. So if we see it here, after performing this C2 axis of rotation, we will get an equivalent configuration which we got after performing the C2 axis of rotation, the C2 operation. So here we have E C2 sigma H sigma V, and I have some doubt with this molecule. I'm not very much confirmed about this, the operations in this molecule. I'll confirm and will get back to you. But this is what I have been thinking. So I will confirm it once again. Okay, and we'll discuss it again in the next session. So let's go ahead with next molecule, which is cyclohexene Br2 Cl2. So I'm taking chair form of cyclohexane here. Firstly, I will show you a representation of it in the plane. So the chair configuration for this is like this. So I'm labeling it as, okay. So here we have this fluorine, this bromine. These are bulky atoms, so we will have to make the configuration such that the steric hindrance between these atoms is minimum. So I'm keeping them alternate, like one is if this bromine, which is bulky here, it is on axial position. So here this bromine will go this chlorine atom, like because they are alternate to each other. Here you can see. So this should go in equivalent position, or sorry, equatorial position, and like this. So this is the representation for a cyclohexane, form, chair form of cyclohexane for this bromine and chlorine substitution. So here we can see we have an inversion center present in this molecule. So how will we get the configuration after this? So these hydrogen atoms. So these positions. So this was if I label it like this: one, two, uh, two, three, four, five, six. So after we go here, two, three, four, five, and this one is six. So bromine, this chlorine was down here, it will go up there, and now this will go down. So these are the configurations we get. So in this molecule, we have only identity operator and inversion of center. No other symmetry operation is present. So here we have order of 2 for this molecule. And the last example I'm going to discuss is tris ethylene diamine cobalt 3. So here we have C2 axis of rotation, passing through each of these bones. And we also have C3 axis of rotation here. Passing through the center of this cobalt, this central molecule atom, cobalt, and coming out of the plane. So here we have C3 axis of rotation, 3 C2 axis of rotations, and identity operation. So the order is 5 here. So these are some of the molecules I wanted to discuss. So if you have any doubts or anything you want to ask, you can ask me now. Our class will go up to 7 p.m. So we have almost 30 minutes left now. You can tell me if anything we can discuss. Uh, so I'll be sharing the recording and the notes for this session and for the last session also, which I will be repeating. Like I'll be recording it for you, and if you have any doubt, you can post it in the discussion forum. So I'll wait for 5 minutes. If not, then I'll try to solve some other problems also. So, any one of you would like to solve this question? This will, would like to find out the symmetry operations in this molecule? Uh, Gayatri, Mayuk. Yes, right. What else? Do we have a proper axis of rotation in this molecule? Like who answered Mayuk, right? Okay. So here we have an inversion center around which we can exchange the positions of these fluorine atoms, these two nitrogen atoms, and also we have a C2 axis of symmetry also, which is perpendicular to the plane of the board. And since this C2 axis of rotation is perpendicular to the plane, we have a plane of board. So we have a horizontal plane here, which is the plane of the molecule, molecular plane. So here we have identity operator, C2 axis of rotation, sigma h, and we will have S2 operation also. Right. Thanks, Mayuk. So this is the isomer. We have a cis isomer also for this. So what are the symmetry operations in this molecule? Mayuk, would you like to answer? And Gayatri, so we have a C2 operation, C2 axis of symmetry here. Yeah, right, Mayuk. Thank you so much. So this is the computation we will get after performing this C2 operation. And do we have a plane perpendicular to it? Like, do we have a horizontal plane here? No, because it will be like this. Then we should have these fluorine atoms like this, which is not the case here. So we don't have a sigma H plane. Neither we have an inversion center here. And do we have vertical planes? Yes. Yeah, we have sigma V. Vertical planes like this and the plane of the board. So here we have 2 sigma V. This is sigma V2, sigma V1. This molecular sigma V2 is molecular plane. So here we got E, 2 sigma V and C2 axis. So the order is 4 here. So any molecule you would like me to discuss? Same as H2O, we can take Cl2O. Benzene boat form, cyclohexane boat form we can take. Benzene is plain up. So let me discuss this OCl2. So here we have a C2 axis of symmetry, uh, and we have and two sigma V planes. One is passing like this, cutting this oxygen atom into half, and these bisecting this oxygen atom and giving these two chlorine atoms opposite to each other. And one is molecular plane. So, like you can have a rough idea of proper axis of rotation. Firstly, so basically, there are certain geometries, like you can say PF5. So if you have trigonal bipyramidal geometry, you can go ahead and find out if it has this C3 axis of rotation and all. So you have to match it with certain geometries, or firstly find out the geometry the molecule has. So if it has trigonal bipyramidal geometry, then you will get same uh, proper axis of rotations and same number of planes in that molecule. So when you will be practicing these molecules, it will get easier with it. So you will have to mm, segregate these molecules based on their geometries, like octahedral, then tetrahedral, or some like we have similar to water. Like here in this case, this cis difluorodiazine, it has symmetry similar to water. So you have to compare these molecules with certain geometries, and then you can find out the proper axis of rotations. So it comes with the practice. The more number of molecules you try out, the it will become easier for you. So we had this two vertical planes here, and so we have E C2 to sigma V. So order is equal to 4 here, and so you wanted me to discuss both form of cyclohexane, right? So I can see a C2 axis of rotation here. Like if I take the center, C2 axis of rotation, and then we have this sigma V passing through this at this carbon 1 and 4 and bisecting the bond between second and sixth carbon and third and fifth carbon. So it will become like this. 1, 4, 3, fifth, second, sixth. Okay, so we have a sigma V plane. This is the sigma V plane here, and also we have a sigma V plane like this also. And fifth. So the proper axis of rotation is C2 here, which is coming like this. So do you have a like sigma h, like if we make a sigma h here, let me show you how will it come. It will become like this, inverted, because C2 axis of rotation, we have these four atoms in the plane and this one and fourth atom above this plane. Like I can show you like 1, 2, 3, 4, then 5 in front of it, and then 6. So if this is C2 axis passing through the center, and if you're going to invert it like perpendicular to the plane, then we will get an inverted geometry which is presented here. So we don't have a sigma h plane here. Okay. So these were the doubts, and any other thing you want to ask? Nickel chromide molecular. Sorry, I didn't get what kind of, is it a complex, and can you write it like the formula for it? Yes, Gayatri, what are you saying? Like you're saying that this uh, board form of cyclohexane has inversion center, or are you asking something else? Uh, no, I don't think it has an inversion center because See, this is the center of the molecule. So you have a carbon atom here, but do you have a carbon atom opposite to it? See, these atoms are present, like are not in the plane. We don't have an inversion center here. Gayatri, what are you trying to ask? I'm not getting it. The axis of rotation which is present in this molecule is C2, which I have shown you already. So this is the C2 axis of rotation, which is passing through this molecule here. Okay. So this sigma v vertical plane, this plane always passes through the principal axis. That is, it must contain the principal axis of symmetry on it. This plane has the principal axis of rotation on the center of it. Okay, okay. Any molecular combination is involved in this rotation. You're asking, like, are you asking for improper axis of rotation, like C2 followed by sigma, like a reflection along the plane perpendicular to it. So we don't have like improper axis of rotation in this molecule. See, this is the C2 here. So I was saying we will have a plane. We don't have improper axis of rotation here, but I will show you how I'm saying this. So see, this is the C2 here. This sigma v vertical plane, this is passing through the center of this molecule. Like this is 1, 2, 3, 4, 5. So this is the C1. Then just try to like imagine this molecule this way. This is C1, then C2 at the back, in the same plane C3, then C4 at the same plane as carbon 1, and then fifth atom here and the sixth atom here. So this C2 plane is passing between the center of this molecule. So after performing this sigma V1, the configuration we will get is 4, 1, 3, 2, 6, 5. Okay, so this was the first vertical plane, and the another plane is bisecting these carbon 1 and carbon 4 atoms and the bond between second and sixth carbon and third and fifth carbon atom. Like not the bond, like the plane is this plane This sigma V2 is like this. So do you get it now? These sigma V planes. Yeah. The improper rotation of molecular symmetry. You were asking, right? So firstly, we will have to perform the operation along principal axis of rotation, which is C2. So after performing this, we got this configuration. C2. So if after this, we will have to perform an operation like we have to do the reflection perpendicular to this along a plane perpendicular to the principal axis of rotation, which is C2 here. So after performing this S2 operation, improper axis of rotation, you were asking, we got this configuration. Are these two configurations similar? Are they equivalent? No. Here we can see a complete inversion of geometry. By inversion, I mean to say this molecule is inverted, these atoms are inverted. It doesn't mean that we have an inversion center. So we don't have inversion of improper axis of rotation here. So the molecule of lithium, Gayatri, I'm not getting your question. If you want to ask and be very specific about it and mention the molecular formula for it. If you can do this, then I'll try to help you. You can post your doubts in the discussion forum. I will try to help you there also. but please mention that the doubts you are having are from interactive session or the main course lectures, so that there are no confusion in that. And I'll be sharing the recording of this session and the notes also. Okay, so you might have registered on the course, and there you might be getting a link for the ask questions. So click on that and then there join the group. Okay, and you might have got instructions for it also. So the time is over now. If you have any other doubts, we can discuss in the next session, and you can also write in the discussion forum. I'll be sharing the recordings and the notes. Okay, thank you. Thank you so much.